U. It's not something that you can calculate directly. As is shown here, the value that you will get a different. You will not be able to get an absolute value. Oh dear, why can't I write on this PowerPoint? Okay. You will not get an absolute value. You will get delta U, only delta U. Most of the time, you need to calculate it yourself. It's not given in a table form. Normally it's not given. So you have to calculate it, and this is the equation to calculate it. But for this chapter 7, you're not going to do any calculation. The data are given. So you're not going to do any calculation. In chapter 8, then you will start calculating using this integration. Okay, using this integration, you will start in chapter 8. So let's go to our next slide. Again, enthalpy. Enthalpy is the same thing like internal energy. You cannot calculate it directly. Let's get my marker pointer. Let's see. Okay. You need to get. Can you see my pointer, guys? Let me go back to enthalpy. Can you see my sorry, I'm going backward. Okay. Can you see my the cursor?
Yes, doctor.
Okay, you can calculate only delta enthalpy. You cannot calculate at the absolute value. Again, the same as internal energy. So delta enthalpy is the difference between a reference point that you set. The same as your internal energy. You have to set a reference point. For example, I give a very general example. I want to go to KL. I'm now in Skudai. If I set my reference point in Skudai, so my mileage will start 0 in Skudai. By the time I reach KL, that's the total mileage I have traveled, which is the difference between the distance from Skudai to KL. That's the difference. But if I set my reference point somewhere in Malacca, for example, Aikro, then my difference is from Malacca or Aikro to KL. So that value is different. Even though I start from Skudai, but if I set my reference point in Malacca, then my value of the mileage when I reach KL is not going to be the same as when I start in Skudai. So I have to set a reference point where I start. And that reference point, or normally we refer to as reference state when you're dealing with chemical, is always set as 0. So just like my example just now, I start from Skudai, I set my speedometer to 0. So by the time I reach KL, I will know how much mileage I have taken to travel from Skudai to KL. But if I start from Skudai, but I set my mileage in Malacca, then the amount of mileage is not going to be the same, because my reference point, my starting point when it's set 0 is not the same. So that is important. When you do energy balance, you need to have a reference state. Where you set it to be 0 is your reference state. Okay, I did mention that last week, but I emphasize on it today. So again, when you talk about enthalpy, have a look at my cursor. When you talk about enthalpy, you will need to calculate it. That will be in chapter 8. But in this chapter 7, the enthalpy is given, because we're not going to introduce the calculation yet. We're going to do it slow and steady. So we're going to look at steam table today. But before you look at steam table, I need to emphasize on this fact that you cannot calculate it directly. Okay, now the enthalpies in your textbook are given from appendix 5, B5 to B9. Some of them, just like is shown here, table B8, you have a specific enthalpy, kilojoules per mole for gases. Now have a look. In this table B8 is specifically for gases. Okay, your reference state, or I need to highlight this. Your reference state is as written on the table. That's your reference state. Your gas. The phase is gas. The temperature, the pressure should be given. It should be given. You have to specify. So reference state at a temperature of 25, where is 25 plus 25? All the enthalpies for these gases are set at 0. It has to be set at 0. After that, if you go below 25, it will have a negative values. the enthalpy will have negative values. But if you go beyond 25, your enthalpy will be positive. Just like if I start from Skudai, but I set my speedometer at Malacca, then from Skudai to Malacca, my mileage is going to be negative. But from Malacca to KL, it will be positive. That's how it works. Okay. Any questions? Any questions?
It's clear, Dr.
Yeah, good. Okay, let's proceed. Now, your reference state, I did mention about that just now. Your reference state is all about the difference in the value. You cannot have one value. You cannot have an absolute value. That's the exact word. You cannot have an exact value. So you only have a different value. So if you look at, if I can get my pointer, oh dear, I can only get, I'm trying to get, okay, that's a different value. Okay, your reference state just now, it's like that table just now, the reference state is at 25 degrees C. Okay, so in this case, if you look at this steam table, this is appendix B5 for saturated steam. The reference state, look at the value when your enthalpy is 0. Okay, when your internal energy is 0. So when it's 0, that means at that temperature, at that pressure, that's your reference state. And what state is it? Water, liquid water. It's not steam, it's liquid water. So your reference state is liquid water at a temperature of 0.01 and a pressure of 0.0611, which we mentioned last week. That's the triple point. That's the triple point. I'm not going to write it. It's having difficulty if I'm going to write it. Okay, that's the triple point. So that's for steam table. Remember, that's the reference state. Now, over here, you have the value of U, internal energy there. You even have the, you even have the specific volume, and you even have the enthalpy there. Okay, another thing I need to point out, steam is in the form of vapor. Now, the heat of latent heat of evaporation is the difference between that value, the enthalpy of the steam, minus the enthalpy of the liquid. So if you look here, 2501 is exactly the same. Your enthalpy of vaporization. You have covered this in when you're doing chapter 6, I think, when you're doing your material balance, is the enthalpy of the vapor, of the steam. Sorry, that is vaporization, guys. That's not vapor, okay? That's vaporization. Okay, this is enthalpy of steam minus enthalpy of liquid. Small h is for liquid. So that is for liquid and that is for steam. Okay, so that's the latent heat of vaporization. That value is for that value. Okay, okay, any questions? Let's just recap what we have done last week. So today we're going to start. We did example 7 to 1. We did example 7 to 2. And we did this example. We mentioned about closed system. Okay, I understand that some of you use the 3rd edition textbook from the internet, the version from the internet. Please remember that we're going to use this equation that's from the 4th edition. We're going to have the equation slightly different. The equation going to be slightly different because of the positive sign. So please take note of the difference. If you're using the 3rd equation, the 3rd edition is negative. We're going to use the 4th edition. So it's going to be positive. Please take note of that because our sign for work is going to be positive when it is going into the system. Okay? Q, or heat, is also going to be positive when it is going into the system. Please remember that you need to really stick to this sign or this labeling so that your answer is going to be the symbol will be going to be the same. Okay, with what we with how we calculate our energy balance. Okay, we're going to stick with the 4th edition. Please remember that. Okay, closed system. The same equation. Most of the system in the industry is not closed. Most of the system in the industry is not closed. Why is it not closed? Because when you have a closed system, nothing can enter it. The mass cannot enter it. Only energy can enter and come out of the system. the mass cannot come in, the mass cannot get out. So in the industry, normally you have an open system. Okay? So when you look at an energy balance, when there is no change of velocity, that means there is no acceleration, the change in the kinetic energy is going to be zero. I did mention about this. And when there is no change in height, your potential energy is going to be zero. Your kinetic energy is zero when there is no acceleration. When do you know you need to calculate kinetic energy? In the problem example that we have looked at, when there is the diameter of the pipe is given, when the diameter of the pipe is given, obviously you need to calculate kinetic energy. That's a hint. That means when the diameter of the pipe is given, the diameter of the pipe is given, that means you need to calculate the kinetic energy. Just like the example that we did before. Now, if your system temperature and the surrounding is the same or it is well insulated, then your heat is going to be zero, which is referred to as adiabatic. When there is no moving parts, that means your work is zero. When there is no electrical current or radiation. But for both of these, normally we do not come across it. We just look at moving parts. That means there's no turbine, there's no pump, work is zero. When there is no change in temperature, no change in phase, internal energy is going to be zero. Okay, so that's more or less what we're going to cover. Okay, so let's proceed to the next slide. We did this, example 7331. Now, an open system. The difference between the previous equation and this equation is, the previous equation for open system and closed system is the delta H. This is the difference. If you are in a closed system, you have delta U or internal energy. You have that. The dot signifies that is per unit time. If it's there is the cap per unit mass or per unit mole. Yes, that's why you multiply it with mass so that you get unit time. So there's a difference in the symbol. The dot means per unit time. It's a rate. If it's there's a cap on top of your enthalpy, that means it is per unit mass or unit mole. Okay, so again, take note. This is positive. We're going to stick with this equation, positive. So we already mentioned about the kinetic energy being zero when there is no acceleration, potential energy being zero when there is no difference in height, Q is equal to zero when it's adiabatic, when there's no parts turning, when there's nothing is moving, then your work shaft, this is shaft work, is zero. Yeah. So that's more or less what we covered last week. So we're going to look at something new again today, but it's not just a few examples. We did this example. Okay, this is one example. Okay, let's see. First question. Have a look at this example. You are given the data is for saturated methyl chloride. I'm going to stop this. I'm going to show you my other slide. Not the slide. I'm going to show you guys my... Okay, whether you can see this. Yeah, this is not what I want to show you guys. Oh dear, hold on. I'm going to go the example just now. Where is the example? Let me have a look. Okay, this is the example. Yeah. Can you see that, guys? Okay. Good. Now my question is the question from that problem. The data is for methyl saturated methyl chloride. The first question is, what is the reference state? Guys, what is the reference state? Anybody? What is the reference state? Oh,
Negative 40 liquid,
what liquid?
negative 40 Fahrenheit.
Okay, liquid. Why do you say that?
Because the internal energy is zero.
Where is the internal energy?
The enthalpy. The enthalpy is zero.
That's the enthalpy, not internal energy. Okay? The enthalpy is zero. So it's liquid. What liquid? It should refer to saturated metal chloride. Okay, saturated metal chloride. And let me try to get, oh dear, okay, no problem. Stick with this. And what else do we need to specify when you are looking at reference state? What else do you need to specify, guys?
Temperature.
Beside the liquid, saturated metal chloride, what else do you need to specify? Okay, let me,
Temperature.
sorry,
Temperature.
temperature. Okay, you saturate liquid, saturated metal chloride. That's the state. Sorry, silap, wrong spelling. Chloride, liquid, and temperature is what temperature?
-40 Fahrenheit.
Okay. And what else do you need to specify?
The pressure
Pressure. What is the pressure?
6.87 BSIA.
Okay, PSIA. Okay, that's it. You need to specify that every time you write you solve your energy balance, you need to specify your reference state. This is your reference state. Oh, sorry. I need to undo that. That's not temperature. Let me erase that. That's not temperature. That is reference state. Yeah, reference state. You need to specify that. If you do not specify that, you will lose mark. Because just like I mentioned that example just now, traveling from Skudai to KL, you need to know exactly where you start. Your mileage depend on where you start your speedometer. When you set your speedometer equals to 0, it's important because if you mention to somebody else saying that, okay, I travel this 130 kilometer to KL, that person will be able to know from you say 130 kilometer from south, down south, so that somebody can really know where you start your speedometer from. So it's really important. Okay, so if you do your calculation for energy balance, you must write your reference state beside the basis. Okay, now the second part of the question, calculate your delta U and your internal energy and your difference in enthalpy. So over here in this table that is given, you don't have the internal energy given. You only have the enthalpy given. So let me erase. No, I'm not going to erase. If I erase that, I'll be getting. I will delete the whole table. Now let's calculate the difference in the enthalpy first. But before that, it should be from a temperature of 50 to 0. You have saturated metal chloride vapor. You're looking at vapor. There's a difference. This is liquid. These two are vapor. So really need to know what you're looking at. Okay. So now you start. Let's put this over here. Your starting point. Your starting point is your initial temperature is equals to what, guys? What is your initial temperature?
50.
50. Okay, 50 degrees Fahrenheit. Your final temperature?
0.
T is equal to 0. Thank you. 0 degrees Fahrenheit. Okay. Again, just like I mentioned, delta H or delta U, internal energy, is always from the final to the initial. So I'm going to denote this as 1, this as 2, in order not to write too much on the screen. So that will be easier. Okay, now this is a difference. So enthalpy of final, which is 2, minus enthalpy, specific enthalpy of the initial, which is 1. Why are we looking at specific enthalpy? Because it's asking for the difference in the specific enthalpy. So now let's have a look. What is the value of the final at 0 degrees Fahrenheit? 0 degrees Fahrenheit, that is the 0 degrees Fahrenheit. You are looking at vapor, so that is the enthalpy at the temperature of 0, which is the final temperature. So that will be 196.23 minus the initial temperature, which is 50, and the enthalpy at that temperature is 202.28. So if you calculate that, what will you get, guys? Let me see whether this is from the textbook, the answer from the textbook. The answer from the textbook is minus 6.05. The unit, take a note of the unit. The unit is BTU per pound. The answer from the textbook is negative 6.05. Anybody, can you double check the calculation?
Yes.
Yes, it's correct.
BTU per pound. Thank you. Pound per pound. Okay, that's English unit. That's the answer for your difference in enthalpy. So let me go to, sorry, I did not supposed to do that. I'm going to the second page. Okay, you have the, oops, I need the table actually, and this here I don't have the table. Let me go back again. I need to get the table. Let me get this table. I'm going to copy that so that I can go to the next page and paste it over here. Okay, so that's it. Paste. Okay, now we can solve the second part. Oops. We need to solve what? Delta U, the difference in internal energy. Anybody know how to calculate this?
Uses the formula del H equal to del U plus PV. Solve for del U.
Okay, good. PV. Okay, that's the formula for the calculation of internal energy. Sorry, the calculation for, is that internal energy?
No,
No,
it will be
that's wrong because of the sign.
sign minus.
Minus. Okay. It should be minus. The equation, if you look at your notes, is like this. Enthalpy is equals to delta U plus delta PV. That's the equation. So now we need to calculate the internal energy. So we're going to get this. It's going to be negative here. Yeah. So let me erase this equation. So we're going to calculate it. What do we have for delta H? Just now is negative 6.05. The unit is BTU per pound mass. So whatever is the unit for PV, it should be BTU per pound mass too. You cannot have a different unit. Because if you have two different unit, you cannot deduct or you cannot subtract, you cannot multiply, or you cannot plus what. You cannot do the sum. That's how you're going to put it. Yeah. Delta PV is equals to PV final value minus PV initial value. Okay, your final value is going to be at what temperature just now?
50.
50. Final value, okay, at 50. So your P is here. That's 51.999. I'm going to erase that because I need to do it somewhere. Let me see. I can do this over there. Hold on. I'm trying to get it bigger. Is there any way I can get it bigger? No, I can't. Okay, let's just sit here. Your pressure is now 51 because I need space in order to cancel the unit. PSI. Sorry.
I think the second state is when Weber at 0.
Okay. Now let's look at our first. Your final state is 0. 0, not 50. Thank you very much for pointing it out. Okay, so let's go to our second page. Your final, this is, I need to write it down or else nobody will forget about it. This is your final state. Yeah, sorry, I'm not doing well here. Okay, this is state 2. This is 2. Oh, I can't write. Why can't I write there? Okay, final state, just right here then. Final is equals to 0. Ouch. Something wrong. Why can't I write? Oh dear. I seem to get nothing Nothing seems to be writing here. What's wrong with my pen? I'm not getting anything. Okay, there's something there. Why is my pen not working? Okay, I'm going to change my pen first. Sorry about that. Not sure why. Okay, your final state is 0. Your initial state is 50. Okay, don't forget about that. So your tap pressure for the final is at what temperature? The what pressure? 18, isn't it? 18.9 psi. Yeah, not very good at this pen because the other pen is better. What is the volume for the final state? That's the volume. 4.989. What's the unit? Feet. Oh dear. I'm really struggling with this pen because this pen.
Doctor, it's 4.969.
Okay, hold on. I'm having problem here. Ouch. Oh dear. Hold on. I'm having problem because I cannot reduce this. This seem to be doing lots of things unnecessary thing here. Okay, it's 6.9. Okay, let's undo that. Because I'm using my previous pen is better for me. 6.9. This pen is not that exact. Okay. What is the unit? Feet cubic per pound mass. Okay, I'm messing up because I'm not used to this pen. I'm used to the other pen. Okay, now, how are you going to cancel the unit? Guys, how are you going to cancel the unit? Anyway?
Using
Okay.
gas constant.
Sorry?
Using gas constant.
Gas constant. Okay, that's it. PV. We got to remember the gas constant. So this is in English unit. So we need to look at the gas constant in English unit. So if you look at your textbook, for those who have your textbook, at the back page, you have the gas constant. Where is the gas constant? At the front, at the back cover. Okay? Yeah, at the back cover. You have gas constant, and for SI unit BTU, you have BTU. The last one written there is BTU, and the one for you got to get rid of BTU. So you have the BTU. You need to get it in BTU, not get rid of the BTU. So that will be 1.987. Anybody that don't have the textbook, you need to look it up later on. BTU, pound mole. Oh dear. Pound mole. And the temperature is in Rankine. So that is equal to, you get to get rid of the PSIA. So you have to look at the gas constant with PIA, that is 10.73. I don't have enough space. I need to undo that. I really wish I got my other pen is working. What happened to the other pen? PSIA. And what's the other unit? Pound mole. Is it? Pound mole. Degree ranking. Yeah. So everything is there. You cancel your PSIA. You cancel your pound mole ranking. Whoa. What happened to the feet cubic? Why is the feet cubic there?
Doctor, the 10.73 is feet cubed per PSI.
Okay, I don't have the feet cubic there, isn't it? Feet cubic. So cancel the feet cubic. So that's it. Pound mass, same unit as over here. So what's the answer? If we multiply the whole thing? What's the answer, guys? I hope my pen works. Oh dear. Anybody manage to get the answer, Tan? What's the answer? Multiply everything up. It should have the same unit as our difference in enthalpy, or else you cannot multiply or you cannot deduct it. So what's the answer, guys? The unit should be in BTU. What happened to my pen?
17.39, Doctor.
17.39.
39.
Hold on. 17. I cannot get something on my piece pen. I think something is wrong. 17.39 BTU per pound mass. That is the difference in the value of PV. So putting that value over here, over to for our calculation of delta U, that's 17.39. 17.39 BTU per pound. Your answer will be
Negative
negative.
6.0.
Sorry. The textbook,
Negative 12.34.
4 point?
12.34.
No.
They're based on this calculation because I got different value for the PV.
Ah, okay. What did you get?
A bigger value than this.
Okay, now hold on. The answer in the solution is negative 4.96, isn't it? The answer in the solution is negative 4.96. Why do we get a different value?
Change in PV. You
Because we don't have final pressure.
Yes. Do you know what's wrong? This is your just the first part, which is this part.
Yeah.
Yeah, we haven't got this part yet. Yeah, we haven't got that part yet. So let me erase this. This is not the right answer. Yeah, so we need to get that part. So if now I need to go to the next page. Okay, I still have it. I still have space. Let's do the second part. This is not equal. This is minus the second part. So let's erase this part. We remember that value 17.39. Is it a different value? Somebody say it's a different value. Minus. We have the minus sign. We need the minus sign. So now let's go to minus the second pressure. No, the initial pressure. The initial pressure is what temperature? Guys? What is
50 degrees.
Okay, so pressure 51.99. 51.99. So we need 51.99. Do the same thing. 51.99. I'm not going to write the unit this time because we already know how to cancel the unit. And volume 1.92. Yeah. 1.92. We need to multiply with the gas constant 1.987 divided by 10.73. That's our gas constant. So the initial value that we managed to get was, somebody gave that value just now, 17.39. So for the second part of the calculation, what is it? For this part of the calculation, what is the value?
18.48.
Sorry?
18.48.
18.48? 18.48. The rest of you guys, double check the calculation. And what the answer is, please. Minus.
Minus 1.09.
09. Thank you very much. That's BTU per pound mass. So go back to our initial calculation. We need to put minus there's a minus sign before it, so there's a bracket, minus 1.09. So your final value is going to be what? Minus what? 4.96, just like the solution in the textbook. Okay, the answer given in the textbook. So that's your final value. Okay, minus 4.96. Any question, guys, on this problem? Anybody need clarification? Need to ask anything,
No,
please?
no, no.
Okay, good. How about the rest of you guys? Is it clear? Yeah, good. So if okay, let me proceed with our next example then. Yeah. Okay, I did mention if you okay, let me unshare this. Oh dear. Stop sharing this. Let's go to our PowerPoint. It's a bit slow. My okay. Now let's go to our PowerPoint. What do we need to cover next? We have done this. Yeah, we have done this. Here over here, I have on this slide. If you take a note, if I can scribble, let me try to scribble. I'm having this is quite slow for me. Okay, this is the where is the PSI just now? That's the PSI. That's the oh, how come I cannot get anything? This is weird. Why am not? Can you see the cursor, guys? Can you see the cursor? I'm trying to get it to write, but I cannot write anything on it. Oh, I don't know why. Okay, this is the value. Okay, now I managed to get it. That's the value of our gas constant that we used just now, and the other value with BTU is that value. Okay, that's the one that we just used just now. These two gas constant in order to calculate convert it into BTU per pound mass. That's what we did just now. Okay. Now let's go to our next topic. So far, you look at a few examples whereby you manage to calculate the value of the enthalpy because the enthalpy are given. So we're going to do the same thing over here, but now we're going to look at specifically at water. Why water? Because water is the most common component being used in the industry. You have steam, you have liquid water, they are always being used in the industry. And you have lots and lots of data available in the steam table that has been done over the years. So it's already completed. So you don't really need to calculate anymore the enthalpy for water, and you don't need to calculate the internal energy for water. It's already been done, so it's available. So you're going to use that data. Okay, so before we look at the data, have a look at this slide. If you look at this slide, it's the phase diagram of water. Okay, and you will notice that you have, this is pressure versus temperature. This side of the figure. Okay, now at 100 degrees C, that's the boiling point of water at 1 atm. If you are at different pressure, the boiling point will be different. So this is the normal boiling point. So in this diagram, this curve, sorry, I'm not doing very well. That curve there is the saturated line. Over here, if you are on this side of the diagram, if you're on this side, on the left side of the diagram, that is saturated liquid. If you're on this side of the diagram, on that line, on that saturated line, you are saturated vapor. So that means this is vapor. Yeah. This is liquid. Oh dear, not getting. Ouch. What happened? Completely gone everything. Oh, I'm not going to record. Okay. I'm going to do all over again. Right, this is terrible. This is really terrible. Okay, you guys have looked at this before, have you guys? Phase diagram. Anybody? Have you looked at this before?
Yes, yes, doctor.
Yeah, okay.
Yeah,
This is water. The water is the one on the left side. Oh dear. The water is one on the left side. Why I'm not getting the pen? Okay, that's water. And this is vapor. Yeah. So if you are on this side of the of this line, you are saturated vapor. If you are on the other side of the line, you are saturated liquid. You can both of it depend on where you are, on which side you are. You could be saturated liquid or you could be saturated vapor on the same line. Okay, so that's what the steam table will have saturated liquid and saturated vapor, and you also have superheated steam. There's superheated steam. Superheated steam is when it is at a very high temperature. You will have supersaturated steam. Okay, let's look at the next slide. Yeah, this is the value of your enthalpy versus temperature. Yeah, so if you look at this, you have two parts to the diagram. This part is the saturated vapor, saturated water. If I can get that, that is saturated water. And this part you have, where is the saturated steam? Here you have saturated steam. Yeah, so over here you have saturated steam. Over here is saturated water. And in between, you will have a mixture of liquid and vapor. You will have in between here. That's the heat of vaporization, the one that I show you guys how to calculate just now. You will get the enthalpy of your steam. You'll get your enthalpy of your steam. If I can get it down here, that's the enthalpy of your steam, and that's the enthalpy of your liquid. So the difference is the latent heat of vaporization. Superheated steam is also given. Subcooled water is a liquid that is below its boiling point. So this is superheated steam that is above its dew point. Okay, any question? That is your bubble point. That is your boiling point. That is your dew point. Dew points mean the first bubble that appear is the dew point. The first drop. The first drop. If you're from steam, you go down. That's the first drop. That is dew point. And if you're from liquid, the first bubble, that is your bubble point. That's when you're saturated at bubble point. For liquid, that's you saturated vapor at the dew point. Any question? Very difficult to talk when I'm showing, it's very difficult when I have to explain, but you guys, I can't see you guys. I'm not sure whether you're understanding me, whether you understand or you don't understand. You guys, how are you doing?
Doctor, it's
Yes.
clear, it's clear.
Good,
We
thank you.
understand. Yeah.
Thank you. I need to get some response from you guys. Okay, now, this is example 752 from the textbook. So if those who have the notes, you need to have a steam table. Okay, you need to look at steam table. This is example 752. Let me get my notes, my pad. Let's stop this sharing so that we look at this example. Oh dear. After this example, I will give you a 5-minute break. Ouch. Not getting it. Why? I'm not getting it. Okay. Can you see, guys? The example 752. Yeah. So in this example, you need to find the vapor pressure, the specific internal energy, and the specific enthalpy of saturated steam. You're looking at steam, specifically steam, at a temperature of 133.5. You are looking at saturated steam at 135. You need the vapor. Let me write down what we need. We need to find the vapor pressure. The vapor pressure. We need to find the specific internal energy. We need to find the specific enthalpy. Yeah. So I have over here the saturated steam table. you need to find the temperature of 133, and it so happened that 133.5 is there. Can you see the table, guys? It's quite small, kind of small. Let me try to zoom in. Whether it's possible to zoom in. Ouch. Not possible to zoom in. Not possible. Okay, can you see the table? Guys?
We can value.
Yes, yes, but not clear. Not really clear.
Not, but
Yeah.
I'm trying to get it to zoom in, but I'm not successful. I'm not really good at trying to get it. I'm not getting it anywhere. Let me see if I can zoom in. Okay, that's better. Can you see that now? Is that clear?
Yes, doctor.
Yeah, yeah.
Doctor.
Yeah,
Yes.
doctor.
I need to zoom out now. Let's see. I'm struggling with this because I'm not getting it done. I cannot get it done. Okay. Anyway, that is the temperature. We need to find the pressure. Let's look at the pressure. There is saturated steam. The pressure is always alongside the pressure is, oh dear, why am I not getting, I'm trying to move. Okay, that's the pressure. Okay, the pressure is here in bar. The unit is bar. At that temperature, the corresponding pressure saturated. This is saturated. That is the saturated pressure. So that is going to be 3 bar. Okay. Next, you need to get somebody left. The internal energy. The internal energy for this saturated steam. So we need to look at internal energy. Oh dear, I'm trying to move, but I'm not doing it very well. How can I move it? Okay. Where is internal energy? That's internal energy. Okay. And we're looking at steam. So you need to look at that value. Let me zoom in again. Oops. Oh dear. My finger is not doing the job that I want it to do. Okay. That's the internal energy of your steam. And you need to find the enthalpy. The enthalpy, this is enthalpy. You're not going to look at water. You're not going to look at evaporation. You're going to look at steam because the question specified that it is steam. So that's your enthalpy for saturated steam. So you have all the 3 values that you need just by looking at the steam table. You don't need to do any calculation at all. Any questions? Any questions? Any question, guys?
Clear.
Here.
No, but
No question. Good. I'm having problem to squeeze it down. I mean, to get it, unzoom it. Okay, that's it. That's better. I can unzoom it now. Somehow my finger is not doing the job. Okay. Okay. You have the temperature, you have the pressure, you have the internal energy, and you have the enthalpy there. Everything is there. Okay. So that's the second example we're going to cover. And I will give you 5-minute breaks. Come back at 9. Right now my time is 9:12. In 5 minutes, so it should be 9:17. Come back and we resume our lecture. Okay, guys, take break 5 minutes, please. Thank you.